If you were to see a line of code which said np.transpose, it takes in an array and then it specifies 3012. What does this do? We spent a long time discussing the theory of convolutional neural networks. It's now finally time to put it to practice. Here we'll do some image classification using CNNs. We'll try to identify the digits in street view house number. So we have a number of images which have been captured using Google's Street View. These are real world images of house numbers or block numbers. We want to identify the digits in these images. Now, as you can imagine, this is a far more complex problem than the MNIST handwritten digit database. Let's see how convolutional neural networks perform here. The MNIST dataset, which you've seen before, comprises of digits written on checks. The digits are far clearer and are in grayscale. Here, the digits are in color and they are not as clear. We'll write the code for this convolutional neural network in the street view house numbers underscore image classification underscore CNN's notebook. The import statements for this demo remains the same as before. The only change here is that we've imported something from the SciPy library. SciPy is a specific Python library for scientific computing. In addition, SciPy is a Python based ecosystem of open source software for mathematics, science, and engineering. The packages such as NumPy, Matplotlib, SymPy, and Pandas all belong to the SciPy ecosystem. If you want the SciPy library specifically, you'll simply use pip install to get it. Now that you're dealing with images and not just numbers, it'll be useful to plot these images when we explore our data, which is why we'll use the Matplotlib library. Matplotlib is a Python two-dimensional plotting library which produces very high quality figures. It can be used in IPython notebooks, and you can plot the images inline if you specify Matplotlib inline like I've done here. You can see the versions of the various packages that I have installed. Just in case you have any problems with the demos, make sure you match up the versions and see if there are any differences. The Street View House Numbers dataset is available from the Stanford website, which you can access right here, ufldl.stanford.edu/house numbers. And here is the URL to access the house numbers dataset, the training path as well as the test path. Notice that each of the files are .mat files. These are files that have been exported from MATLAB, and this is why we need the SciPy library. The SciPy library gives us a library function which allows us to load MATLAB files and extract the image array information that we need. Once again, let's go ahead and automate the process of downloading this data into our current working directory. I'm going to call the training dataset house numbers underscore training.mat and the test dataset house numbers underscore test.mat. There's really nothing new in the code that we write to download this dataset. It's exactly the same as before. We use the URL lib library from 6moves, which abstracts away the differences between Python 2 and 3. One heads up though, when you call this download underscore data helper function, these files are pretty huge and it might take several minutes to download, so please be patient. The Stanford Street View House Numbers dataset comes in two different flavors. First format is more complex. It comprises of the original image with bounding boxes around the actual digits. The second is a simpler format where every image is a cropped digit which is 32 by 32 in size. In this particular example, we choose to go with the simpler format, though once you've built your convolutional neural network, you can test it out on the original dataset and see how it performs. One thing to note though is that some of these numbers may contain distracting digits to the side. So it may contain more than one digit where only one of the digit is the focus or one of the digit is the significant digit in that image. Every image can have one of 10 possible classes as its associated label. There is one class representing each digit. Digit 1 has label 1, digit 9 has label 9, but digit 0 has the label 10. This becomes important when we set up our convolutional neural network. So remember that 0 is represented by the label 10. Let's load in the data from the MATLAB file. We'll do this for both training as well as test data. spio.loadmat is the function. This will simply read in the MATLAB file into the train underscore mat and test underscore mat variable. While loading this data, we specify the squeeze me parameter to be true. Squeeze me set to true basically sets up all the one dimensional matrices, that is, any one by one matrix that exists within the data that we've loaded, are squeezed to be scalars. In the data that we just read in, we won't have any unit matrices, that is, one by one matrices. They'll all be scalars. Let's explore the format of the data that we just read in. Train underscore mat is of type dictionary. Let's see what its keys and values are. The keys that we're interested in are the x variables and the y labels. The x variables represents the matrices which form the images, and the y variables are the labels. The remaining are metadata. We can just ignore those. We'll just extract the x and the y variables, the data that we're actually interested in, and assign it to x underscore train and y underscore train and the corresponding variables for the test data. X data and y data are clearly arrays, but what is the shape of this array? How is the data laid out? The training data set comprised of images is basically a matrix which is 32 by 32 by 3 by 73257. The first three dimensions are the dimensions of a single image. Every image is 32 pixels by 32 pixels, and because this is a color image, it has three channels, that is, three values to represent the value of a single pixel. The last dimension, 73,257, is the number of images that we have in our training data. The Y labels, on the other hand, are simple arrays. The training data is around 73,000 images and the test data is around 26,000 images. In order to feed this image data into our convolutional neural network, we need to reshape the data a little bit. We want the axes to be in this order. The first axis represents the number of images, the second, the height, then the width, and the channels in the image. This we can do by performing a simple transpose action on the original data that we read in from the file. Transpose basically rearranges the axes of your matrix in the order that you want them to be. We want axis at index 3 to be first. The axis at index 3 was originally the number of images. That will now be our very first axis. And then we have the height, width, and number of channels, that is axis at index 0, 1, and 2. That was for the training data. Apply the same transformation on the test data as well. We'll choose only a subset of our training dataset in order to run our training process. That's because if you use all the 76,000 images, the training process takes really long. The resulting machine learning model will be much better, but for a simple demo, 10,000 images should be sufficient. So choose the first 10,000 images from our training dataset. We'll also evaluate our model on a smaller set of images from the test dataset. Instead of using all of the 26,000 images, we'll just choose 1,000. Now pick the first 10,000 labels from our training data and the first 1,000 labels from our test data corresponding to the images that we've just chosen. Let's examine the shape of our training data here. So we have 10,000, that is the number of images. Every image is 32 by 32 with 3 channels. We can access a single image by indexing into this matrix. X of train of 0 is 32 by 32 by 3. I'm going to go ahead and write a simple helper function that will display this image on screen. This simply uses the plot library from matplotlib and calls imshow. It passes in the digit, which is just our 32 by 32 by 3 matrix. This will just display a single digit on screen, as you can see. This is a digit from our training data set. The digit at the center is 1, that will be the label for this image. There is a distractor though. 9 is also present in the same image. Let's go ahead and view one of the images from our test data as well. You can see that this image is a 5. As you can see from both of these examples, that the images are more complicated than simple MNIST images, which means the classification will be correspondingly tougher. Let's quickly explore how the labels for our training data looks. As you can see, It's just a simple array of numbers. These numbers are the labels for the images, the digits that the images represent. np.transpose basically allows you to swap around the axes of the array that you pass in. Here, the array is represented by the variable arr. Every axis within an array can be identified by an index. The very first axis is at index 0, and the fourth axis here in this four-dimensional array is at index 3. When we rearrange the axes of this array, we want the last axis at index 3 to be at the very beginning, and then come the axis at index 0, 1, and 2.